Recording.
Okay, welcome everyone to this session of the seminar on PDEs and applied mathematics. Today we have the honor and pleasure to have with us Professor Francesco Fanelli from the Basque Center for Applied Mathematics, BICAM in Spain. He obtained his PhD from SISA in Italy and Université Paris in France. Then he obtained several postdoctoral positions in BICAM, Université Paris in France, and Scuola Normale Superiore in Italy. Later, he worked as a maître de conférence at Université Claude Bernard in Lyon, and nowadays he is a Ikerbasque Research Associate Professor at BICAM. We can say that his area of expertise is theoretical analysis of PDEs, focusing on well-posedness of PDEs arising in fluid dynamics, singular limits in the context of geophysical fluid flows, and the study of hyperbolic operators having low regularity coefficients. Thank you very much, Francesco, for having accepted our invitation to give this talk, and all yours.
Thank you very much, John, for this introduction, and thanks to all the organizers for the kind invitation. It's a great pleasure for me to be here and honor also and to present this talk today. So thanks a lot for this opportunity. So in this talk, I would like to speak about a system of equations arising in fluid mechanics, and more precisely describing the dynamics of a fluid which is assumed to be non-homogeneous. So there are variations of the density, and ideal in the sense that there is no viscosity, there is no friction force acting between molecules of the fluid. So the fluid flows essentially just driven by pressure forces between molecules. Okay, the precise system of equations we are going to study in this talk is the following one. So we describe the fluid by three unknowns. Rho, which is a scalar quantity which is positive and represents the density of the fluid. U, which is a vector field, d-dimensional, if the fluid is moving on a d-dimensional domain, which is the velocity field of the fluid. And there is another scalar field, which is the pressure, which represents the pressure of the fluid and which is denoted by capital Pi. Okay, according to the principle of conservation of mass, the density evolves through a continuity equation. And actually, this continuity equation is written as a transport equation driven by the velocity field u. It becomes a transport equation because u is assumed to be divergence free. So there is the third equation which says that the fluid essentially is incompressible. So the divergence of u, this is encoded mathematically by the constraint that divergence of u is equal to 0. Then there is an equation for u itself, and this equation can be derived, for instance, from Newton's second law applied to a fluid parcel. So it says that mass times acceleration is equal to the forces acting on the fluid parcel. Okay, the mass here is mass per unit volume, so precisely the density, rho, which multiplies the acceleration, and the acceleration written in the so-called Eulerian variable take this form. So there is a time derivative of the velocity field plus an advection, a transport, u times gradient applied to the components of u itself. And the balance of forces, since we are neglecting viscosity, are just pressure forces, and these are potential forces. So there is plus gradient of this function pi equal to 0. Okay, so this is the system, and we call this system density-dependent incompressible Euler. We will see why in a second. Throughout this talk, we will assume the following as we are interested in the initial value problem. So we fix initial data. And in order to simplify the discussion, we will work on the whole space Rd, where the space dimension d is greater or equal than 2. Okay, so we have to fix initial data, and the initial data ρ0, u0 satisfy the following assumptions. So u0 will be assumed to be divergence free itself. So the fluid is at the beginning is incompressible. And ρ0 is assumed to be bounded, so bounded by a constant rho upper star. And also, very importantly, it's bounded away from 0 by a positive constant rho star. So this physically means that there is no vacuum initially. And actually, these L infinity bounds for ρ0 are preserved by the transport equation. So for any later times for which the solution exists, one is able to say that row of t remains in between these two constants. So there is no vacuum at any time. Okay, of course, there is a very special situation in this picture, which arises whenever these two constants, rho star and rho upper star, are equal. Okay, so if they are equal, the initial density becomes constant, and by transport, it remains constant for any later time. So the equations, which are the density-dependent Euler, degenerate to the so-called, which is the celebrated system, incompressible Euler equations, which maybe you have already heard about. So these writes as these equations are divergence of u equal to 0 and dtu plus u scalar gradient of u plus gradient of the pressure equal to 0. These equations are very well known and broadly studied in many contexts. It's far from my scopes to make a full panorama of the results available for this system. I just want to recall three main results, which are a cornerstone of the theory of the incompressible Euler equations, and whose counterpart is not known to hold for the density-dependent case. So the first result I want to mention is the so-called Bill-Kato-Maida continuation criterion or blow-up criterion. It depends how you state it. This is due to Bill-Kato-Maida in 1984, and this states the following. So let me write some details. So I go to the blackboard. In order to state the Bill-Kato-Maida solutions for regular solutions of the incompressible Euler. So in order to state it, let me introduce the vorticity, which is, so the vorticity can be defined in any space dimension. Let me stick to the case dimension 2 or 3, because this is the physical case. So the vorticity is defined as the curl of the velocity field u. Okay, and okay, this is in 3D, but you can define, so in 2D in particular, we use the same symbol, but it degenerates to a scalar function. So it's no more a vector, it's just a scalar. And this is d1 of the second component of u minus d2, the first component of u, in dimension d equal to 2. Okay? Okay, the Bill-Kato-Maida continuation criterion says that the solution can be continued beyond a time capital T, if and only if the integral between 0 and capital T of the L infinity norm of the vorticity is fine. Okay, why this is important? It is important because to some extent the incompressible Euler are quasi-linear transport equations, and the classical continuation criterion for this kind of equations requires a full control of the L1 in time, L infinity norm of gradient of u. But what Bill-Kato-Maida says is that it's enough, in fact, to control only a few quantities, which are the derivatives appearing, the combination of derivatives appearing in the vorticity function. So I stated it in dimension 1 or in dimension 2 and 3, but actually it holds in any space dimension. And okay, and actually we will see that in dimension 2, it's the importance of this result is really in dimension 3 and high. So this is the first result I wanted to mention. So a blow-up criterion resting on the vorticity. Okay, the second result I want to mention is that in space dimension d equal to 2, in fact, the solutions, smooth solutions, are known to exist globally in time. Okay, one way to prove this is using the Bill-Kato-Maida continuation criterion plus another ingredient which I will mention in a second. But actually, this result is known since Volibner in 1933. Okay, so global results in dimension d equal to 2. The third result I want to mention is the so-called Jurovic theory in the case of space dimension d equal to 2 again. So Jurovic theory is a theory of weak solutions at the level of the vorticity, which says the following fact. So I go back to the blackboard. So in space dimension d equal to 2, if one fixes an initial vorticity, which is in L1 cap L infinity, then there exists a unique solution to the incompressible Euler for which the vorticity is so there is a unique global solution for which the vorticity is L infinity with values in L1 cap L infinity. Okay, so it's the two characteristics of Udovich theory are that the solutions are unique, despite these are weak solutions at the level of the vorticity. The solutions are unique and they are globally defined. Okay, so both global results in dimension equal to 2 and Udovich theory rest on the following property, which is specific to the two space dimension, that the equation for the vorticity in 2D is very simple. So starting from the equation for U, one can compute an equation for omega, and the equation for omega in dimension 2 reads as a pure transport equation by the velocity field U itself. Okay? Of course, the nonlinearity and non-locality of the equations haven't disappeared because U itself can be recasted in terms of omega by the so-called Biot-Savart law. So this is written in two space dimension as minus gradient perp of minus Laplacian minus 1 of omega, where gradient perp is a notation for denoting the rotation of angle P over 2. So it's minus D2 D1. Okay, probably should write it here. Okay, so despite we still have nonlinearity because U is a function of omega, so this term is nonlinear. Despite we have non-locality because we invert the Laplace operator, still the equation is a transport equation, so one gets preservation of LP norms. And this is crucial, in particular L infinity norm. And this is crucial to prove both global existence, think for instance to the Minkowski criterion, and uniqueness for an argument which is slightly more important, okay? But this preservation of LP norms in dimension equal to 2 is crucial. Okay, so these are the main results. Let me go back to the non-homogeneous system. So here I remind you the equations. Recall that now we have a density which varies, this rho. And let me try to explain why these results are not known to hold in the density-dependent case. Well, in order to understand this, it's in fact enough to consider the vorticity equation in dimension d equal to 2. Okay? So doing that, we can divide the equation for u by rho and apply the curl operator. And so we see that as in the classical case, where rho is constant, we have a transport structure for omega, for the vorticity, which is a scalar, I remind you, in dimension 2. But there is an additional source term, which depends both on the density and on the pressure. Okay, so there is 1 over rho square, gradient perp of rho times gradient of pi. Okay, actually, so why this is a problem? Well, because first of all, gradient of pi is a quadratic quantity. Already in the homogeneous case, it's a quadratic quantity in the velocity field. And even worse, the gradient of rho evolves and grows exponentially with respect to the velocity field, if one wants to propagate regularity. So since this growth is superlinear, the growth of this term is superlinear, it's clear that if one wants to prove global estimates, well, there is a problem. Okay, if you think in terms of growth, well, you do not have a global result. You need to remain at short time in order to control uniformly the norm of the solution. And sorry. No, una charla. Arriva in una puerta e possiamo. Sorry. Okay. Good. So no global well-posedness results. at the same time, if we are thinking to propagate low regularity norms of omega, so if we want to prove a result of the style of Udovich, we would like to propagate L infinity norm of omega, of the vorticity. Okay, now in order to control the L infinity norm of omega, one needs to control the L infinity norm of this source term, gradient perp of rho, gradient of pi. And in particular, one needs an L infinity norm over gradient of rho. But now, by transport theory, the gradient of rho grows exponentially. So the typical growth is, the typical control is that the norm of gradient of rho in L infinity grows exponentially with the Lipschitz norm of gradient of U. Okay? There is exponential growth in the Lipschitz norm. So in order to say that rho is in L infinity, gradient of rho is in L infinity, one needs U to be Lipschitz, and this is more or less constrained by transport. But if U is Lipschitz, actually it's more regular than in the classical theory of Udovich. So one immediately quits the framework of Udovich and goes to a stronger framework. So this makes Udovich theory inachievable in some sense, at least with this approach. The failure of the Bill-Katomida continuation criterion is a little bit more subtle, so I will try to detail it later on. Okay. Okay, so what is known for this system? Actually, so I spoke about coupling of quasi-linear transport equations. The same structure you see is inherited also for the density-dependent system. So any space which is embedded in the space of globally Lipschitz functions is good a priori to solve the system. So you can work in, this is indeed true, so you can work in HS space, CK alpha, you can refine this by tangential regularity approach and so on. So you have local well-posedness in these spaces which are embedded in the space of globally Lipschitz functions. Okay. Since these results are local, one wants to understand what happens to the time of existence. And actually, there have been in the literature some continuation results, continuation criteria. The best one which I want to focus on now is due to Bailey and Shin, which is a refinement of the previous ones. And this states precisely what I mentioned before. So the solution can be continued beyond a time capital T if and only if the L1 in time, L infinity in space norm of the full gradient of U is bounded. Okay? Good. And this is true in any space dimension. There is nothing specific to the 2D. On the other hand, in 2D, we see that we are not very far, at least if rho is close to a constant, the system is not far from the homogeneous one. So one would like to see better results. And in fact, it's possible to prove in dimension 2 that the lifespan of the solution, which I denote by Tmax here, is bounded by a strange nonlinear function, which depends on the norm on a critical norm of the initial velocity, but which has a correction, which is a double logarithm of 1 over another critical norm of gradient of rho 0. So this means in particular that if gradient of rho 0 is small, so if we are close to the homogeneous, the time of existence becomes larger and larger, which is consistent with what is known for the incompressible Euler, for the homogeneous incompressible Euler. Okay, so this result is specific to the space dimension d equal to 2. And to some extent, it's an asymptotically global well-posedness in the sense that when rho 0 goes to a constant, we get larger and larger time of existence, and eventually global whenever rho reaches the constant value. Okay, let me mention that, so I spoke about local well-posedness. In fact, let me mention that in the literature, there is also one global well-posedness result, which is in the context of asymptotic stability of Couette flows. Okay, so one starts with very small perturbations around the homogeneous profile, which is very specific, which is a Couette flow. So rho tilde is equal to 1 and U tilde is equal to Y0. This is the Couette flow. And you assume to be close to this homogeneous stationary solution of the incompressible Euler. You require Gevrey regularity of the perturbations, a very specific geometry of the space, and then you can prove global existence. So it's a result which holds true in two space dimension in a very specific setting, yet it's a global well-posedness. To the best of my knowledge, the only global well-posedness for our system. But the general picture for general data is still open. There is another global well-posedness result, but in presence of a damping term in the velocity equation, so it's somehow a different story, okay? So I will not speak about this. Okay, I would like now to state our main results. In order to motivate them, let me go back to the continuation criterion I presented for the density-dependent Euler system. So I said that a smooth solution of the density-dependent Euler can be continued beyond a time capital T if and only if the L1 in time, L infinity space norm of gradient of U is under control. So let me remark that this continuation criterion requires a control on all the components of gradient of U. In order to establish well-posedness, global well-posedness or blow-up, one needs to check all the entries of the gradient of U, of the Jacobian matrix of U. So one needs to control this square minus 1 quantities. Minus 1 because we have one constraint, which is the divergence-free constraint. So we need to control this square minus 1 derivative, quantities, let me say. In particular, in dimension d equal to 2, this reduces to 3 conditions to be verified in order to establish global well-posedness or blow-up. Okay, let me highlight that the Bill-Kato-Maida criterion, what could be a corresponding result of to Bill-Kato-Maida should require only one condition, because the vorticity it's a scalar quantity in dimension d equal to 2, and the Bill-Kato-Maida requires a control only on the omega, so only on a scalar quantity. Okay, but why Bill-Kato-Maida is so difficult to establish for the density-dependent Euler? Well, because essentially because of the possible growth of the higher norms of the gradient of rho, okay, which you need to control if you want to propagate regularity. Okay, when you try to estimate, for instance, the HS minus 1 norm of gradient of rho, well, you apply your preferred method, you find a term which is gradient of rho in L infinity times U in HS, so the norm that you want to control. Now, either you keep this gradient of rho in L infinity in your continuation criterion, or you try to estimate directly it. But whenever you try to estimate it directly, well, you find precisely the growth I wrote there. So there is an exponential growth, okay, in the Lipschitz norm of gradient of U. And now you can make, you can work a little bit in order to erase somehow this exponential growth, but you can do that at the price of getting norm of U in HS square in this term. Let me not give you the details, but you can do that. But whenever you have a quadratic growth of the norm you want to control, you have lost in your continuation criterion. Okay, you want to close estimates applying grow wall and keeping the exponential the low regularity norms, but now you have U in HS to the power 2, and this argument does not work anymore. So so far you need the 3 conditions in dimension 2. Bill-Kato-Maida, which would need one condition, it's difficult to expect to hold, but at least with this approach it's not clear that you can prove it. The first result I want to present is that in fact it's enough to control just 2 quantities in order to establish, not 3 but 2 quantities in order to establish global well-posedness or continuation or blow up. So the first statement is the following one. Let us, and this is specific to the 2 space dimensions. So let me take d equal to 2, and let me take a regularity index S larger than 2. This just because I stated the theorem in the framework of Sobolev spaces. But actually the statement holds true in a more general framework, which is the framework of Bezov spaces. And then you have other conditions on S. But whenever you restrict to HS spaces, S becomes larger than 2. Okay, good. Then we take the same assumptions on the initial data I fixed before. So rho 0 bounded and bounded away from 0. Divergence of u0 equal to 0. And now the third assumption is to set the problem in a well-posedness framework. So a framework in which I know that the system is locally well-posed. So I take u0 in HS and gradient of rho 0 in HS minus 1. Okay, and then there is a last assumption, which in the framework of Sobolev spaces is satisfied for free, just by embeddings. Okay, but if one wants to move to other frameworks, this assumption is needed. And this assumption says that there must exist a P0 larger than the space dimension 2, such that gradient of u0 is in LP0, so has some integrability. Good. Okay, these are the assumptions. So let me define Tmax, the lifespan of this local solution, of the local solution associated to this initial data. And let me introduce the vector field X, which is gradient perp of rho. Okay, so it's minus d2 rho, d1 rho. And I define the operator of differentiation along the direction X to be just X scalar gradient of the components of U. In dimension 2, you have two components then. Okay, the result says that the lifespan is finite. If the lifespan is finite, then the integral between 0 and this lifespan, Tmax, of the L infinity norm of this quantity, the xu, must blow up, so must be equal to plus infinity. Okay, so the other way around, if this integral is finite, you can continue your solution. Okay, this is true in more general setting, and in particular, you can reach the critical regularity case. So in the framework of Sobolev spaces, this would be S equal to 2, up to work in Bezov spaces. And in this case, you can state a similar result, but first of all, you need to replace the L infinity norm by a stronger norm, B0 infinity 1, which is at the same scaling of L infinity, but which is slightly better. And moreover, you are not able to say that the integral must blow up, but there is a pointwise condition, which is stronger. So the lim sup approaching the Tmax must blow up. Okay, good. Let me make a few comments about this statement. So the first remark is that this result is in fact in agreement with what is known for the incompressible Euler equations, the classical case, rho equal to constant. Why this? Well, because if the two constants, rho star and rho per star, are equal, rho 0, the initial density is constant, and as I said before, by transport, the density remains constant for all times for which the solution exists. So this vector field X, which is gradient perp of rho, becomes a 0, it's degenerate. And then the integral can never blow up, and then one recovers global well-posedness for the homogeneous system. Okay, the second remark is that so this criterion requires to verify two conditions. So the equivalent of the Bill-Kato-Maida, which requires only one condition, remains open. It's not known to hold. To some extent, however, this can be viewed as a sort of Bill-Kato-Maida continuation criterion, in the sense that we do not need to control the whole gradient of U, but only the components of the gradient of U along specific directions, only combinations of derivatives of U. Okay, not the whole gradient, but only combinations of derivatives of U. However, with respect to the Bill-Kato-Maida continuation criterion, this criterion is nonlinear because it involves a product of derivatives of rho and U. And in addition, this has a geometric meaning because we are not considering all the derivatives of U, but just the ones which evolve along a specific direction. This direction, capital X, which itself evolves according with the flow. So these are the derivatives along the tangential lines, the level lines, sorry, of the density. Okay, so there is a specific meaning of these derivatives. Okay, there is another remark to relate this to the so-called conormal regularity allachement, but this is more technical, so I will not enter into these details. Okay, okay. Let me try to state the second class of results I would like to present. And these concern the possibility or impossibility of prove a sort of Udovich theory for the density-dependent Euler equations. Okay, so now the assumptions will be just to push down as much as we can the regularity of the previous assumption. So I will still assume the initial density to be bounded and bounded away from zero, and we will simply take a gradient of rho zero in L infinity. We take an initial velocity field to be of finite energy and divergence free. And we assume the initial vorticity to be LP0 and L infinity, because of course we have in mind the Udovich, okay? So P0 here is larger than 2 as before, and for technical reasons it must be smaller or equal than 4. This is more or less the equivalent of Udovich setting, apart from this assumption of finite energy of L2 control over U0. But this is not a this is physical and this is not very a big deal, I would say. So we have two kind of results, which is sequential stability of smooth approximated solutions and the uniqueness of solutions at this level of regularity. But both results are actually conditional results because they hold under an a priori geometric information, which is precisely the same condition I presented before in the continuation criterion. Okay, let me try to state the two theorems and then I will stop there. So assume that the first one is sequential stability. Assume to have a sequence of smooth solutions, for instance, the ones we constructed before, rho n un gradient of Pn, smooth solutions on some time interval 0 Tn. Of course, this depends on n. You can get them by approximating the initial datum. Okay, so you smooth out the initial datum, you construct smooth solutions. They are defined a priori up to some time Tn. The geometric assumption is that you assume that there exists a positive time, which is smaller of all the Tn's, and for which this geometric quantity integral between 0 and capital T of dxn un in L infinity is bounded uniformly in n. Okay, so we have a uniform control on this geometric quantity. Xn here is the gradient perp of rho n. Okay, under this condition, you can prove that you converge weakly star to some target profile, rho u gradient of pi. I will not enter into the details, but this target profile is defined on 0t times R2, and this target profile verifies more or less the same conditions of Udovich theory. Okay, so it's consistent somehow with the picture of Udovich. And moreover, this triplet solves the density-dependent incompressible Euler and the vorticity formulation, which I presented before. Okay, so in some sense, they are to be taught as the equivalent in the density-dependent case of the Udovich solutions. And the uniqueness statement says that you can have at most one solution. So under the assumptions I presented before, which I recall here, A, B, C, you have at most one solution, one triplet, your rho u gradient of pi, on some time interval 0t times R2, such that the same conditions as before are satisfied. I'm sorry that I didn't detail them, but so you have at the same level of Udovich, say, you have only one solution, but you need an extra condition, which is not guaranteed from the previous result, which is that your profile itself must satisfy this geometric information. So the integral between 0 and capital T of the xu in L infinity must be finite. Okay, so you see that we have an additional assumption to add. So these are conditional results. Okay, so I think I have no really time to say something on the proof. Let me just say that the basis for proving both results is to prove some LP estimates for the vorticity and for the gradient of rho. And this is achieved by a new method, which was not explored before. So the first one is that, I skip, the first idea is to propagate the information of a gradient of rho by looking at the evolution of capital X. And the equation for capital X actually is better than the equation for simply the gradient of rho because it makes this geometric quantity appear for free. Okay, the second idea is to use the momentum instead of the velocity field. To control u, one uses the momentum, which is rho times u, and its vorticity, which I call eta, so the curl of m. Of course, there are drawbacks, which are not very bad, but there are also good points, and in particular, the fact that the equation for eta reads very simple. You have no pressure, and you have this geometric quantity which appears again. Okay, so one can establish LP estimates and then go either to the Udovich results or to the blow-up results. And so I prefer to stop here, and I thank you very much for your attention.
Thank you, Francesco, for your excellent talk. So, okay, thank you very much. We will give the opportunity to the audience if they want to ask any question or make some comments. So if you want to ask something, you can open the micro and or write in the chat if not. Okay. Is there any question? Many people here clapping. And yes, I have some questions because this topic is everything new for me, and I was writing some curiosities. Well, first of all, thank you for your talk and the introduction explaining the origin and the terms of the equations. It was good for people that are not familiarized with that. And then one curiosity is maybe you have mentioned, but you said you mentioned the quote flow. No, the quote flow.
Yes.
What is that? What type of flow is that? Because I don't know.
So
So
quet flow is
it's a type of flow with a
it's a type
specific
of flow.
application.
It's a type of special solution, special stationary solution of the incompressible Euler in
Uh-huh.
the homogeneous case. And it's, I think,
You mentioned something about
I
rho
hope
equal
not to
to one,
be.
no?
Hmm?
You mentioned something about rho equal to one when you were
Yes, because so if
characterizing
you
that.
take the homogeneous profile, density profile, you get precisely the solution of the homogeneous incompressible Euler. And
Mm,
so you have a precise stationary solution of your density dependent system because essentially you reduce it to a stationary solution of the homogeneous incompressible Euler.
mm,
And actually, there is a huge amount of literature about these kind of stationary solutions, saying that if you linearize the equations close to to these stationary solutions, actually you get what is called implicit damping. So you get extra decay properties of the solutions, and you can prove global existence close to these profiles with the specific, both, so 2015 proving global well-posedness for incompressible layer close to QET.
mm.
But this typically requires, so you are able to extract decay if you consume derivatives. So this is why you typically need Geoffrey regularity to prove these results. So somehow this work extends this literature to the case of density
This,
dependent flows.
but maybe I was a bit lost. And what is exactly the Bill-Kato-Magda criterion? What is it
Okay,
based on?
so
If it can be explained simply.
so as I said, the typical blow-up criterion is to say that you need to control the whole gradient of u in L1 Lipschitz. So I mean gradient of u in L1 L infinity.
Mhm.
Okay, and this is typical for hyperbolic problems. Here you have the pressure which introduces non-locality, but from the mathematical point of view, from the point of view of estimates, you are pretty much close to quasi-linear hyperbolic theory. the Bill-Kato-Maida continuation criterion says that instead of considering the whole gradient, you can consider only the vorticity, these special combinations of the gradient of u. So this is because actually the importance is in 3D and higher dimensions, because in 2D global existence you knew it from before. Okay, and okay. Yes, there is a technical point in the Bill-Kato-Maida continuation criterion which says that you cannot control the L infinity norm of gradient of u in terms of the L infinity norm of omega. You have a logarithmic interpolation inequality. This is crucial. You cannot control it simply by in this gradient of u in L infinity controlled by omega in L infinity, because gradient of u is a singular integral operator in terms of omega, but you can add a logarithmic correction and you have this result. And then you apply Osgood lemma instead of Gromwall lemma, and this is why you get this improvement from gradient of u in L infinity to omega in L infinity. I don't know if it was clear in...
Yes, it seems very complex for someone that doesn't know, but thank you for the explanation. And the last question, only one curiosity. In the last one of the last theorems that you have presented down in 2025, that one, yes, the theorem, the statement.
Yes.
No, the next one, maybe the one that was appearing capital TN, Sapen, that one. Yes, in the hypothesis that you are writing that the infimum of all TNs are greater than or equal to capital T. I was curious because before you were mentioning lifespan time. Is that capital T related to that in some sense?
Somehow, yes, because it is consistent with the previous result, meaning that you know that all the solutions, since the integral cannot blow up at time capital T, all the solutions are defined up to that time. Okay. However, if you really want to prove this, so this means that so you cannot reach simply by the same norm of the initial datum. You need at some point to split the nonlinear quantity, and you find the integrals of singular integral operators need to switch getting an explicit control. So removing this assumption, so far we can do that only moving in a stronger framework, and which we didn't want to impose in this statement.
Yes.
Okay, so these Tn are not a priori. Nothing prevents you to degenerate this interval to the simple 0 point, and this assumption says that you cannot degenerate. You have a time of existence which is good for all the solutions, and this is consistent with the previous statement indeed.
Yes, thank you very much, Francesco, for the answers.
Thanks.
And is there anyone that wants to ask something more or a comment? If not, we will thank Francesco for your talk and for being here, and we will leave the floor to the next speaker. Thank you,
Thank
Francesco.
you very much.
Yes.
Thanks a lot.